This podcast covers work, energy, and the work energy theorem. To calculate work, we use this formula. W stands for work, F is the force doing the work, D is the distance or displacement that the object makes, and theta is the angle between the force vector and the displacement vector. Here's an example. I push a 100 kilogram desk 10 meters across the floor with a 30 Newton pushing force. It moves at a constant speed because of friction. Find the work done by each of the forces that act on the desk. So let's draw a free body diagram. We have gravity. That's always down, and that's mass times g. Since our mass is 100 kilograms and g is 10, this will be 1,000 newtons. Okay? We also have normal force of the floor pushing upward, and that should be equal and opposite. I didn't quite leave myself enough room, but the normal force is also going to be 1,000 newtons, balancing out the gravity force. Now I'm pushing with a force of 30 newtons. I'm going to say I'm pushing to the right, so I'm going to draw that vector to the right. That's my pushing force. It is 30 newtons. And there's also friction. Friction is going to oppose the motion, and it says that it's going at a constant speed. Constant speed means zero acceleration. Zero acceleration means the net force equals zero. So these two, the pushing force and the friction, also must be equal and opposite. So the friction also has a magnitude of 30 newtons. Now I'm going to indicate the direction that it's moving. It's moving in the same direction it's being pushed. Notice when I draw the displacement vector, I'm not drawing it on the free body diagram itself. The free body diagram is just for forces. So the displacement is 10 meters. Now I'm going to find the work done by each of the forces. The work done by the pushing force is going to be the magnitude times the displacement times cosine of the angle. So the magnitude is 30 newtons times the displacement, which is 10 meters, times cosine, and since the displacement is in the same direction as the pushing force, the angle between them is 0. And cosine of 0 is 1. So this is 30 times 10 times 1, which is 300 newtons times meters, which gives us joules. So that's the work done by the pushing force. Now the work done by friction is again going to be, sorry about that, 30 newtons times 10 meters times cosine of, now we've got the motion to the right, but the friction to the left. So the angle between those two vectors is 180. And cosine of 180, you might recognize, is negative 1. So this is going to be negative 300 joules. So we also have the work done by gravity. That's 1,000 newtons times 10 meters times cosine. Now if we look at the direction, it's moving to the right, but gravity is pointing downwards, so the angle here is 90 degrees. Cosine of 90 is 0, so this is going to be 0 joules. What that says is if the motion is perpendicular to the direction of the force, that force is doing no work. Same thing happens with the normal force. The work done by the normal force is 1,000 newtons times 10 meters times cosine of 90 degrees. Again, it's 0 joules. If we add up all of those and find the net amount of work, it'll be 300 minus 300 plus 0 plus 0. So it's 0 joules in this case. Notice the pushing force in the direction of motion is a positive number. That means by pushing it, I'm adding energy. The friction force is in the opposite direction. It's a negative amount of work. Friction is taking away energy. It's changing it into heat or vibrations, noise, other things like that. Gravity and normal force are not doing any work at all. So here's one that's a little bit more complicated, perhaps. The drawing shows a boat being pulled by 2 locomotives through a canal of length 2 kilometers. The tension in each cable is 5,000 newtons, and theta is 20 degrees. That theta, let me put that in here. It's this angle. This one is also the same angle, 20 degrees. What is the net work done on the boat by the 2 locomotives? So if I call this F1 and it is 5,000 newtons, and this one is F2 and it's 5,000 newtons, the displacement, remember the displacement doesn't go right on the free body diagram. I'm just going to write it over here. The displacement is 2,000 meters. Right? 2 kilometers is 2,000 meters. So let's find the work done by force 1. W1 is going to be F1 times D times cosine of theta, which is 5,000 newtons times 2,000 meters times cosine of 20 degrees. And that is 9.4 million, or times 10 to the 6 joules. Notice that both forces, F1 and F2, have the same magnitude and the same direction, or the same angle relative to the displacement. So we can conclude that W1 has the same magnitude as W2. And since they're scalars, they don't have a direction. So the net amount of work is going to be W1 plus W2, which is 1.88 times 10 to the 7th joules. Here's another one that's kind of similar. I pull a suitcase by a strap. I pull with 37 newtons at an angle 30 degrees above the horizontal. If I move the suitcase 45 meters, how much work have I done? So this angle is 30 degrees. This force is 37 newtons. And the displacement is 45 meters. So if I calculate the work is going to be 37 newtons times 45 meters times cosine of 30 degrees. And if I plug that in, I get 1,400